What I've described so far is voltage control, where an increase in demand voltage results in an increase in speed. It's an inherently stable system, because if the train comes to an incline and the speed drops, Vg will drop and Vs minus Vg automatically demand more torque. The speed will drop, but only to a limited degree. This test setup allows us to see the effect in action. The motor under test is the 250 watt Fasco on the right. It's being supplied with a constant 6.3 volts and is drawing 2.36 amps. The initial load is simply its friction and the friction of the 150 watt Fasco motor coupled to it. The speed is 1295 rpm. The plan is to apply an additional constant torque load to simulate an incline. To provide this load, the 150 watt Fasco will be used to cause dynamic braking. If I simply fed its Vg into a resistor, the braking would reduce as the speed falls. To provide a more realistic situation, I've used an electronic load, set to supply a reasonably heavy stabilized 1 amp load, irrespective of the value of Vg. When the load was applied, the speed fell to 1188 rpm, a drop of only 8.3%. As Vg fell, Vrm, which is Vs minus Vg, increased, and therefore increased the motor current Irm, which in turn increased the torque to partially compensate. I think it's worth showing the equivalent circuit again here. I noticed that in the previous part, sometimes I referred to the motor current as Im, and sometimes as IRM. This was a slip. On this diagram I've used IRM right through. I've also emphasized that Vs and Vg are voltage sources, whereas Vrm is simply the voltage drop difference between them. When applying dynamic braking, the direction of Vrm is reversed, since Vg is then bigger than Vs. There are other possible control strategies. Let's consider current control. If we start off from rest and gradually increase the current, i.e. torque demand, nothing will happen until the value exceeds the effect of static friction. Then, suddenly the train will begin to move. However, since our current demand is greater than what is required to balance kinetic friction, the train will begin to accelerate. Force is mass times acceleration. Vg will increase, but unlike with voltage control, the electronics will automatically increase Vs in step with it to keep the current constant, so the acceleration will continue until the voltage supply reaches its maximum or the motor brushes start to bounce. We have a runaway situation. However, imagine that on level track we have managed to adjust the current demand to just balance friction. If we reach an incline, there will not be enough torque to balance the increased load. Unless we do something, speed will fall until the train comes to a complete stop. The previous setup can demonstrate this. The motor power supply is now used in constant current mode, and with difficulty has been set to 2.31 amps. The consequent voltage drop across the motor is 6.5 volts, and the speed is 1351 rpm. When the 1 amp load is applied, the speed collapses to 219 rpm because the system cannot call on more current to balance this additional torque load. In fact, the speed would have dropped to 0, but with this particular setup, the electronic load cannot maintain its 1 amp at a very low Vg. This constant current system is very difficult to drive and is never used alone. Now let's consider speed control. This has some similarities to voltage control, but the speed is continuously monitored by a voltage tachometer or an incremental encoder. The measured speed value is then compared with the demanded speed, and the voltage automatically adjusted to make the two equal. However, the electronics can be set up to not quite keep the speed equal to the demand. The difference is referred to as the droop. The droop can be set to give the same response as voltage control. It's a stable, versatile system, but not often used because of increased complexity. We come now, at last, to the control strategy for the 9F. The system is more complex. The load and the tender each have their own motors and can separately provide torque. We have two drawbars, the drawbar dB1 between the loco and the tender, and the drawbar dB2 between the tender and the load. I eventually decided to operate the main source of traction, the tender, under voltage control with some provisos, which I will explain later. The difficulty was how to incorporate the loco. At this point, I invented the analogy of Dobbin and Hercules. This enabled me to discuss the control strategy with people who had no knowledge of electric motors or electronics. A farmer has two horses, Hercules, who is a young powerful horse, and Dobbin, who is a more experienced horse but older and must not be overtaxed. The farmer wants to take a load to market along a level road. Let's consider an initial condition where only Hercules is harnessed to the farmer's cart. The farmer encourages Hercules with a gentle application of his whip. Hercules starts to pull, and once his effort has overcome static friction, the cart starts to accelerate. As the cart nears the speed that the farmer requires, the farmer eases Hercules off, and the horse settles down to match his pull to balance the frictional drag of the cart. This all sounds very like the single loco example described earlier, and inclines or declines are coped with in a similar way. Hercules either pulls harder or resists a downward acceleration, as dictated by the farmer. On the next journey, the farmer decides that Dobbin should do his bit. Since the two horses are not equal, he decides to harness them in series rather than in parallel. For the purposes of this discussion, we shall call the harness between Dobbin and Hercules drawbar dB1, and the harness between Hercules and the cart drawbar dB2. The journey starts off as before and reaches the desired speed, but Dobbin, being an experienced and crafty horse, has realized that if he matches his speed exactly to that of Hercules, he needn't put in any effort at all. In fact, since he doesn't like Hercules very much, he could try to go a bit slower and make Hercules work harder to keep up the speed of the cart. Dobbin also realizes if he tries to go faster than Hercules, Hercules can not only reduce his effort a bit, but a lot. This would result in Dobbin putting in more effort than was good for him. What is needed is a method of control, where Dobbin tries to go a bit faster than Hercules, but his effort is monitored and not allowed to exceed what's good for him, the load being shared out proportionately. This was the problem I had to resolve for my electric 9F. At one point I considered strain gauging the two drawbars and designing the electronics to proportion the pulls. However, I decided that that was unnecessarily complicated. For the 9F, why not just monitor the loco and tender currents? As we know, these are proportional to torque. This was easy to do with Hall effect current sensors. It would not be as accurate as measuring the drawbar forces directly, because the sources of friction in the loco, with its plain bearings and linkages, would be significantly higher than those of the tender. However, on reflection, what I really wanted to do was to limit the load on the teeth of the single 140-tooth gear and the linkages. I was less interested in accurately controlling the loco pull via dB1. Nevertheless, I still did want the loco to make a reasonable contribution and not be a load for the tender. My solution was to operate both the tender and the loco under voltage control, but with these provisos. Firstly, the input to the loco motor amplifier should be set slightly higher than that of the tender. Then the ramping of the demands to both motor amplifiers should be common to both, and each motor amplifier should have its own current limit, but that of the loco should be controlled more accurately and set lower in the region of 10 amps. How this was achieved will be explained in Part 5C.